Well, this is my favorite of the pictures we've seen of the Keck telescopes because Haleakala on Maui is right in there in between. And this was the astronomy picture of the day. I was asked to do a little bit of history. Um, so, does anybody know who this is? You are right. This is Tycho Brahe. Um, so this is going back farther into history than they wanted me to go. He was a Danish astronomer. The king of Denmark gave him the whole island of Wien, which is a little island between Denmark and Sweden, to do astronomy. This, I think, is the first known government support of astronomy that there is. But he was here. This was a meeting. The reason I'm showing this picture is not really this history, but there was a meeting about large telescopes that took place on this island in Wien. And you can see this statue, how big it is. There's participants from the meeting, how tiny they look comparison to Tycho Brahe. But this meeting was about large telescopes. And this is 1996. And while I was decluttering my house, I found some view graphs. Remember them? Used to have view graphs. This was one of my husband's view graphs. This was Hans Boesgaard, who worked at Keck for many, many years. In fact, he started out at the UH with the 88-inch. Anyway, this was a discussion of the differences and benefits of segmented mirrors versus a monolithic mirror. And you can see from this that the benefits of this small mirrors far outweighed the monolithics. I think it was a Gemini telescope mirror came by barge. It went to Kauai Harbor and then it took it 3 days to get up to the mountain. Whereas these other little segments were quick and easy. So all of these telescope projects began in about 1984. But by the time of this meeting in 1996, look at what was going on. Keck 1 had been in operation for 2.5 years getting data, and Keck 2 had just been dedicated, and these other telescopes were far from operation. And of course, we have this guy, Jerry Nelson, who we have talked about a lot, to thank for all of that. I think this is a great picture of Jerry and one of the mirrors. And Jerry, it's a nice young picture of him, but he was certainly a genius and responsible for what we have at Keck today. What we have at Keck today, this is looking at the mirror, but I want to, the mirrors did not grow as hexagons. They started out as nice circles. So they had to have these edges, 6 edges cut off. Those apparently people call the ears. When Hans retired, he was given one of those ears. And those ears that it sat in our dining room on a shelf. And I can show you this great That is my cat Jasper, and he is sitting on the ear, looking out at the Pacific Ocean. So the other part of my excitement about Keck is the instrument of high-res. And here we see Steve Vogt, who is a PI of high-res. And I'm also showing a little picture of the update of the detectors on high-res, so that there were now 3 detectors. And that turns out to be very important for my kind of research. So to get into my research, here is a distribution, the chemical abundances of the elements, starting with hydrogen as a function of mass numbers. And you can see hydrogen and helium are up there. The next 3 items on the periodic table, lithium, beryllium, and boron, are way, way down. And then we go back up for carbon, nitrogen, and oxygen. So what's with that? I can tell you this part, that there are 2 lithium atoms, for every billion hydrogen atoms. There are 26 beryllium for every trillion hydrogen atoms. And then with the 630 boron atoms for every billion. So if we're going to observe those, we have to observe them in the lines that are the strongest, and the lines that are the strongest are the ones that go from the ground state to the first excited state. And for lithium, that is a doublet at 6707 angstroms. For beryllium 2, I mean, look at lithium 1, and beryllium 2, it's also a doublet at 3131 angstroms. And unfortunately, Keck can't do boron because it would have to be in orbit. So we can use these 3 elements to learn a lot of stuff, including the formation of elements, the interiors of stars, and I'll get into that in a minute, and galactic evolution of chemicals. So here's why we can learn about interiors. This is a model of the sun. The photosphere is there as in yellow, as a sphere in yellow. But then where the red circle is, below that red circle there are no lithium atoms, because the temperature is 2.5 million degrees. And as soon as a lithium nucleus sees a proton, it turns into 2 helium atoms, and that's pretty stable. So beryllium suffers the same kind of fate, but it takes 3.5 million degrees to destroy the beryllium. So there's no beryllium inside that blue circle. So we have a small shell that has lithium in it, a slightly bigger shell that has beryllium in it. So that's what's there on the main sequence. But then as the star evolves to become a red giant, that little shell of lithium expands as the convection zone expands. And so the amount of lithium that was in that little shell is now spread out over a much bigger region, so it's effectively diluted. The beryllium, same thing happens to beryllium, but it has a bigger reservoir, so it's not so much depleted. So this is what happens to poor old lithium and beryllium on the main sequence. They get destroyed if they get down to those dangerous temperatures. And as they go on to be a red giant, they get diluted. So what are we going to do? Here is the way, what happens when we try to observe these. This is a spectrum in the lithium region here on your left. It's in a nice clean region of the spectrum. There's a lithium doublet, but it's easy to do. Anybody can do it. I mean, any telescope can can do lithium. Beryllium, on the other hand, it takes a special skill and that Keck had. And I have to say that when Wal Sargent was on that original committee, he really was the one who insisted that Keck be able to go down to the ultraviolet. He wanted to look at quasars and whatever else was down there. So I am the beneficiary of that. But even if we have this terrible problem compared to lithium, we can still do an analysis of beryllium so that the 10 angstroms on your left, we can look at 2 angstroms and we can do a spectrum synthesis. It's not easy, but we can do a spectrum synthesis, and in the several angstroms piece we have 300 lines of all kinds of things. You know, there's vanadium and there's iron and there's OH and all kinds of blending things. But we can do a decent job at extracting a nice abundance of beryllium. Now, I'm sorry for the quality of this particular figure, but this is what I was saying before about the 3 CCDs. The CCD in the UV has a 93% quantum efficiency at the beryllium lines. I've tried to indicate that by the arrow. I hope you can see the line. So that made all the difference in the world for beryllium studies, which we took advantage of. We had a big, the directory on my computer is called Big BE. We had 17 nights allocated to that program. We lost 2. One we lost to a snowstorm, okay, but one we lost to that earthquake. I don't know, do any of you remember that earthquake? Yeah. Yeah? Well, I had that night. And I woke up that morning at Kohala, and I was sitting at the edge of the bed. It was a little after 7, and suddenly everything started shaking. And I ran outside of the house. The house was wood, so it probably would withstand it, but, you know, I went out. And then I learned that, okay, it was okay, except trees had fallen over the road and I wasn't going to be able to get there. But then they called me and they said, we canceled observing because all the light fixtures in the remote observing room fell down. Later we learned there were some difficulties with the dome, and so Keck 1 was closed down for a few nights. But anyway, I did manage to get 15 of those nights, and we managed to observe 117 stars. And so they covered quite a range in iron abundances. And we did a spectrum of the moon so we could get a comparison taken with the same instrument for the beryllium in the sun. And with those spectra, we measured a whole bunch of iron 1 and iron 2 lines, quite a lot of titanium lines, and 3 magnesium lines. Plus, we got beryllium abundances by spectrum synthesis, but there were OH lines not only in the area that was blended with the beryllium lines, but elsewhere in that order of the spectrum, so we could determine oxygen abundances. And so this is what we found as beryllium and iron. As iron is a surrogate for age, we loosely say, and there they are. amazingly well correlated over several, 4 orders of magnitude in iron and 3 orders of magnitude in beryllium. That looks pretty impressive. And, you know, how are we going to account for that? I will explain a little bit later about how we make beryllium. But we see evidence between beryllium and oxygen. So we managed to get oxygen from several OH lines. And there's another pretty good linear relationship between these logarithmic quantities. And then while we're up, we could look at oxygen and iron, forget beryllium for the moment, and look how well they're correlated. But if you look at the ratio of oxygen to iron compared to iron, you see that iron, the ratio of oxygen to iron is higher than it is in the sun at low metallicities by a pretty big factor. But that too is pretty linear. And then we can look at titanium and look at the one on the right, titanium to iron. That is amazing how tightly correlated they are. And we see that as well with the magnesium. And again, magnesium and iron are so well correlated. And the formation mechanism by nucleosynthesis for those alpha elements of magnesium and titanium and oxygen is quite different from the formation for iron. So that was big BE. And now I want to talk a little bit about lithium. And let's start at the beginning with lithium. Lithium was formed in the first 15 minutes of the Big Bang. Okay, and so this shows the reactions, the nuclear reactions that took place. The universe starts with some neutrons and some protons, and it's really hot, and they get together, they stick, and you make deuterium, and you make tritium, and you make helium, and helium-3 and helium-4, and you make some lithium-7. You make some lithium-6, but it turns into lithium-7. And this is one of my favorite demonstrations of that, what happens in the first 15 minutes of the universe. You start out with neutrons and protons, and you can see across here that, where is this? Here, the protons and the neutrons, and you start making deuterium, and so the neutrons go down, and ultimately, through those nuclear reactions I showed on the previous slide, you see that lithium comes up and goes down here. You make some beryllium-7, but as I said, that decays to lithium-7. And then, okay, so this is what? Okay, it's up at the top. This is 1 minute, and then this is 10 minutes, and then everything after 15 minutes is just the same. Until a long time later when galaxies and stars start forming. Okay, so we only have those 3 elements made, and there's nothing else. And it's a very good thing there's nothing else, because we wouldn't be here. Because if you combine helium and a proton, you get mass 5, but there's nothing stable at mass 5. And if you combine helium and helium, you get a mass 8, and there's nothing stable at mass 8. So we're just stuck with hydrogen, helium, and lithium. And you remember that by the time you get to red giants, you get what is called the triple alpha process. So that's 3 helium, and there is no stable mass 8. But in the inside of the star, there's enough beryllium-8 for a helium atom to collide with it, and it forms an excited state of carbon. So we do get what's called the triple alpha process there. So let us now look at this. There is beryllium versus iron and lithium versus iron. And so what we have here, this is the Big Bang production of lithium. And then we get more lithium in the same way that we're getting beryllium all the time here. We're getting more lithium. But you see that there are a lot of stars in this sample that don't have any lithium, or they have a reduced amount. And that's because lithium gets pushed down to the interiors of the stars where it gets destroyed. So here shows you how more lithium and beryllium and boron are actually formed. Since they're destroyed in the inside of stars, they have to be formed on the outside of stars. And that takes energetic cosmic rays swirling around the galaxy, banging into carbon, nitrogen, and oxygen, because there's a lot of those, and breaking it up into little pieces, some of which are lithium, beryllium, and boron. So how do we get primordial lithium? What are we going to do? If we want to find out the actual amount of lithium that's formed at the time of the Big Bang, we want to look at the oldest stars, right? And we want to look at stars that are not evolved, because if they're evolved to red giants, their lithium will be diluted. And so if they're old, though, we have to know their age. And the best way to know their age is if they're in a cluster, because we look at the HR diagrams and we calculate, we compare it with calculations, and so we can tell, oh yes, this is an old cluster. So we concentrate on those guys, and wait, did I go backwards? I went backwards. So here's one of the globular clusters that we looked at with Keck. So this is M5. And we have to look at unevolved stars. You see where our little red stars are. Those are the stars that we observed with Keck high-res, and you will notice that they're 18th magnitude. This is high-resolution spectroscopy at 18th magnitude, and that takes Keck. And in fact, they are multi-hour exposures, although we took them in 30-minute or 45-minute exposures, so we wouldn't get too many cosmic rays landing on the CCD. So those, now I'll show you the beryllium region. One of the things about looking at these old stars, in the beryllium region, you saw all those lines. Well, in an old star, none of those lines are as strong. So that helped a lot. Wait, here we go, right? This is another one of the globular clusters. this is in the lithium region, and you can see these 4 stars have very different line strengths of the lithium line. The observed are the dotted, and then the best fit is that blue solid line. A factor of 2 more and less are the red dashed lines. So you can see from these 4 stars that they don't have the same line strength, even though they have the same temperature. So there's really a difference in the amount of lithium. And this shows it even more dramatically. These are 2 stars in the globular cluster M13, which, are 10 degrees different in temperature? And look at that, there's a big difference in the line strength, a big difference in the lithium abundance. It turns out we have done several clusters, but so have the people with the VLT on this same project. The guys at the VLT have a better time because those southern globular clusters are just brighter. So they have been able to observe more than our meager 5 stars in M5 or whatever. Am I going backwards again? Yes, I am. How do I go forward? This one. So now we have a plot of the lithium abundances. And this A lithium is just is the amount of lithium compared to hydrogen. So hydrogen is 10 to the 12 on this scale, lithium 10 to the 3, but for these clusters it's 10 to the 2. So this is a function of metallicity. First thing is I have all the references on this slide, but you can see there is a big spread. Well, let me go to the next guy. So you see there's a large spread in each of the clusters in the amount of lithium. And you can see that they have a big spread, but they all have stars that are higher than the field stars. Why should that be? We look at metal poor field stars, and the maximum is there about 2.2. But these globular clusters show more lithium in many of their stars, but they don't show as much lithium as is predicted by Planck and WMAP and the Big Bang nucleosynthesis. And I can't read this. So you can, although the maximum isn't as much as what we see in the field stars, the maximum in these 8 clusters now is all about the same. It's all about 2.5, where the prediction is more like 2.8. There's not much connection with the age. They're all old, but it doesn't matter if they're a little younger globular clusters or a little older. It doesn't matter. They still have this big range in lithium. was a puzzle to me. For example, 47 Tuc is known to have multiple populations on the main sequence. But if the stars have evolved, have gone to be red giants or gone to be supergiants, they've lost all their lithium. So you ought to find some on the main sequence of the second generation that don't have any lithium. But we only see a couple of stars in one of those 8 clusters. So that's a mystery, unless supernovae form lithium. So the explanation for the range is, stars start with a little bit of angular momentum. Some stars have more, some stars have less. And the ones that have more, as they spin down, manage to lose their lithium. And so they would have less lithium than the slow rotators. And that is validated by theoretical calculations. So we have learned these various things from, I've just talked about 2 particular studies, the big BE study and the primordial lithium study, but we've learned a lot from Keck, from light elements. So I want to end with a mahalo, because astronomers can't do astronomy by themselves. They really need a huge amount of people to design and to build, and a Jerry Nelson to think it up, and all the support people and the instrument builders and the data analysts and everything. And I want to thank all these, not just the Keck people, but so many people who make astronomy happen, who allow us to do our research. Thank you. Mahalo.